This is the 100th anniversary of the truth table. I'll bet you didn't know that. About 100 years ago, the truth table was invented. So I'm going to do a series of videos from truth tables to 4-bit adders, and I'm going to simulate that with Netica. The only interest in this video, the only value that I'm hoping to add, and it's up to you to decide if I've actually added any such value, is that I'm simulating that with Netica so that we can get an interactive truth table so that you can actually play with a truth table. You didn't know you could actually play with a truth table. And if you can play with truth tables, then you can play with logic gates and you can play with full adders. So that's my objective in the course of the next 3 videos, probably. Moving on, I was looking into the engram for truth table from 1850 to 2019. So you'll see over here somewhere, right there, truth table, are fairly active, has a kind of up and down history, and it goes back to about, sometime in the 30s. But if you go back a little further, you'll see, but there's something in 1920. And in fact, that's why, for a very long time, the truth table was more or less officially designated as having been born in 1921. But there's something else going on over here. Have a look at that. Why is there an engram activity here for truth table in around 1900? Let's take a closer look. Here we are in 1900. Who's writing at the time? There is this guy, Charles Sanders Peirce, the greatest philosopher you have never heard of, who died in the 1890s, I think. And Bertrand Russell, whom you no doubt have heard, said of Charles Sanders Peirce that he was the greatest philosopher that America produced in the 19th century, or in the late 19th century. And Bertrand Russell's student was none other than Ludwig Wittgenstein. And he's the man who is frequently associated with truth tables. But you'll notice that it struggles to be born and then dies, struggles to be born again and then dies. And then, here it takes off. And it takes off in 1938. Thanks to who? Thanks to this man, Claude Shannon, who in 1938 wrote on, a version of the truth table, and he figured out how to translate Boolean truth table into electrical circuits. So, moving on. So this is the earliest truth table from the Tractatus in 1921, and it looks pretty familiar, but it's in German. So W is for true, and F is for false. So for a long time, this was thought to be the earliest truth table, but it goes back really further than that. And it goes back, as I say, to this man, Charles Sanders Peirce. Let me read this from Wiki. He was educated as a chemist and employed as a scientist for 30 years. Perce made major contributions to logic, a subject that for him encompassed much of what is now called epistemology and the philosophy of science. He saw logic as a formal branch of semiotics, of which he is a founder, which foreshadowed the debate among logical positivists and proponents of philosophy of language that dominated 20th century Western philosophy. Additionally, he defined the concept of abductive reasoning, as well as rigorously formulated mathematical induction and deductive reasoning. And here is the punchline. As early as 1886, he saw that logical operations could be carried out by electrical switching circuits. 1886? I didn't know they had electricity, much less electrical switching circuits. But there you have it. The same idea was used decades later to produce digital computers by, of course, Claude Shannon, which was in 1938. So, Let's talk about the size of truth tables, since we're doing the simplest truth table. And in this case, we're going to have exactly one variable. If there are n input variables, then there are 2 to the n possible combinations of their truth values. We've only got one. We're going to call that p, and it can only be true or false. A given function may then produce true or false for each combination. So the number of different functions of n variable is the double exponential 2 to the 2 to the n. So with one variable, p, n equals 1. So there are 2 possible combinations of truth values and 4 different functional mappings. What are they? Let's have a look. The simplest truth table. Moving on. Let us see. Okay, it has 4 truth functions for a single Boolean variable p. What are they? The first one. And keep in mind, right, a function is really a mapping. It's just a mapping from domain of values and to another codomain of other values. In this case, the domain is really simple, 0 or 1. And the codomain is just 0 or 1. And we have some kind of mapping. This one takes 0 to 0 and 0, or rather 1 to 1. The SOAP over there gives it away. And that's, of course, the identity function. Very well. The next function, what does it do? The next function maps 0 to 1 and maps 1 to 0. And that, of course, is negation. It just reverses the value of whatever it gets. Very well. Moving on. The next function does what? It maps 0 to 0. And it maps 1 to 0. Oh, how convenient. That's not much work, really. That's pretty easy. We call it falsity. Could say contradiction. The other one, our last one, again, the SOAP gives it away, maps 0 to 1, and it maps 1 to 1. And that, of course, is going to be the truth function. Sometimes also just called a tautology. No matter what you say, it says yes, true. Yes, true. True to whatever. Okay, the goal now, and this is the point of this video, the goal is to simulate that with Netica. And Netica is a way of creating a little causal network that you can play with. And you didn't think that you could play with truth tables, but you can. And we'll see how that's done. So, onward and upwards with Netica. Okay, well, here we are. So, this is the truth table that we are aiming to reproduce. So, let me remove the finding here. So, true or false, we haven't entered a value, and watch what happens to this and this. So, I'll put true here, and when that's true, well, identity is true, and negation, of course, is false. So this goes down, and that goes up, and that goes up, and that goes down. So I can go back and forth. That's what I mean by an interactive truth table, because it interacts with me. I give it a question, or I give it a value, and it returns a value for me. Notice that logical truth and logical falsity, I've graded them out because they don't say anything. They just sit there, and that's it. They don't do anything. Very good. So let me just show you how I did this, and it's so simple, so simple. So, all right, so I got a head start. I kind of cheated, okay, but all I did here is I just made some nodes, and all I did is I put, okay, well, they're going to be either true or false. And then I called them. I knew what I wanted: identity, negation, contradiction, and tautology. But now here is the key point. This is our mapping. It's an arrow, and that's really all what we're doing, just mapping. We're going to be mapping values from there to there, from there to there, from there to there. Okay. Now, notice, if I compile, okay, if I say true, false, true, false, well, it's a pretty shade of green, but nothing happens. Why? because we haven't said anything to Netica about what it means to return an identity or to return negation. So what we'll do then is, well, we'll just remove all our findings. We'll go here, we'll go into its brain, and then we'll say to Netica, okay, this is a deterministic node, okay? And it's an identity. So when I give you true, you give me true. If I give you false, you give me false. And that's it, right? Sometimes this is called the reflection function because it just reflects exactly what you give it. Okay. Oh, look, and it turns a pretty blue. And that's because I've color-coded deterministic functions to be blue. Does it work? And it does. Cool. I give it true, it says true. I give it false, it says false. That's what identity does. Okay, how about negation? Okay, negation. I'll go here and I'll say to Netica, okay, this is a deterministic node. Now, negation, when I give you true, you give me false, and when I give you false, you give me true. That's it. That simple. And it turns blue because it's a deterministic function. And now let's see if it works. Okay, true. And it gives me true for identity and false for negation. And if I go false, then identity returns false, but negation returns true. And so I go up and that goes down. And I go down and that goes up. There. How cool is that? Now, contradiction and tautology, well, we need to give a mapping for that. And so we say to Netica, okay, Netica, this is what you got to do. Contradiction, if I give you true, you say false. If I give you false, you still say false anyway. So you always return false, no matter what. So we apply, and that's it. And if I go true, you sit still. I give you false, you sit still. You say nothing except false, false, false. Tautology, on the other hand, will always return true. So we define it as such, and we say, okay, well, if I give you true, you return true. If I give you false, you still return true. Done and done. Okay, and now, okay, we go true, and the identity is true, negation is false, contradiction false, and tautology true. And now if we play with it, right, we go up and down, up and down, up and down, up and down, up and down. Okay, it's not much of a game, but still, right? The cool thing about an interactive truth table is that it reacts to what you put in. Right? A truth table on paper doesn't do anything. It just sits there. But that doesn't. That reacts to you. And that's really very good. Now, this will seem really, really very simple, and it is. And it is. So we'll do in the next video a truth table with P and Q, which is just a tiny bit more complicated, but not by much. And what we will see there is that we can easily then construct logic gates like OR and NAND and if then and etc. And obviously it's just a simple step from logic gates to half adders, full adders, and then 4-bit adders. And then who knows, maybe, I don't know, can we simulate a whole computer on Netica? I don't know about that. It would be very cool if I could, but that's for another day. So until next time, bye-bye. Okay, and we are back with the simplest truth table. But I want to leave you with one thought. Is it actually the simplest truth table? You can probably wonder, wait a minute, okay, what if n equals 0, where, oh, no variables? What the heck does that mean? That means that maybe Oh, and I'm giving it away here. Maybe we could have the nothing. Is there a function that maps the nothing into something? I guess you could. You could have the empty set and some mysterious function that out of nothing creates something. And we'll call that 1, the true. And I call that the function g. Gee whiz, what do you think g might stand for? Some mysterious function that creates something out of nothing. So, how about that? I have answered the question. Why is there something rather than nothing? Because of this function g that maps the nothing into something. There. Okay.